Okay. Okay, can you see my screen?
Yes,
Yeah.
I can see the slide.
Yeah, fantastic. Well, as I said this morning, I realized there is no slide in the website of Rob Heinemann for this chapter, so I had to create the slides I had to rush actually through them. So if there is any typo and error, so just please let me know or ignore it for now. So in this chapter 4, we're going to discuss time series features. So in this chapter, we see a couple of sections. First, there is a section dedicated to some simple statistics, which are related to some features of time series we may know, like mean, median, percentiles, and things like that. So following that, there are a section dedicated to some features related to autocorrelation. And following that, we have discussed in previous chapter, so Arnab presented about the composition. So we discussed about STL decomposition. So here there are some features related to this STL, and we discussed them as well. And there are many other features that we can extract from the time series. So in other features section, we briefly look at those features as well. And finally, we look at throughout these sections, we look at actually the examples with Australian tourism data. Again, this is the data set we have used in previous chapters, and you must be familiar with this. So we explore this data set using these features. So, well, first of all, let's see what we mean by time series features. Well, time series features are numerical summarizes computed from the time series. So we have a time series, and then somehow it has a characteristic like a trend, seasonality, autocorrelation, randomness, the thing like that. And we can, using features, we can represent this characteristic of features using a single number or a value. And that's the idea of time series features. And then we do it in this book using a package called FIST. So this is again a part of FPP3. So if you install FPP3, FIST will be installed automatically. It is a part of it. So FIST package in R includes functions for computing a featured and statistic from time series. And this is actually, the name FIST is coming from this. So when time series features are useful, what are the conditions when we say, okay, let's look at the time series features? First of all, if you work with many time series, this is potentially the best way to investigate what are the different features, what are the different characteristics of your time series. And here I'm not talking about 1, 2, 3 time series. Of course, I'm talking about thousands of time series. So if you work in retail industry, for example, or if you look at if you work in supply chain or logistics, if you have a big warehouses, well, that's the condition. You have many time series, and potentially looking at the time series feature is a good option. The second scenario is, sometimes you get a time series, you have no clue what are the features of this time series. If that's the well, of course, you can go and plot and then create different sorts of visualizations to understand. But a really nice way to understand what are the features available or exist in the time series is to extract the feature of the time series. So we can compute many different features on many different time series. And then we can, of course, use this to explore the properties of the time series. So now let's look at some simple statistics that we can extract using FIST package. Well, here I'm introducing basically a sort of a template, what is the function in FIST that we can use, and then what is the template we have here to extract the features. So here you have your data, and this data must be in a teasable format. Okay, it's not a table here, or it's not a data frame. It must be a testable. And of course, if you don't know what is testable, you need to go and read chapter 2. So we take the data, and then we have a pipe operator, then, and this is the function we have to use here to extract features of the time series. Okay, so the name of the function is features. And then following by the parenthesis, you have to provide the name of a variable in your data that you want to calculate the features for, right? So this is the name or the column or variable from your data. And then after, so this is the first argument of the feature, and then we put a comma, and then you have a second argument, and this is the function. Of course, you can ignore this function, and if you ignore this function, then it will automatically calculate all the features for the data. But if you provide a function, and then we show in the next slides what we mean by a function, then it will go and specifically calculate some features for what you need. If I just show you an example with a data set, so here we have the tourism data, then features, and then if you look at the tourism, then you have a measurement called trips. And what I want to do here, I want to calculate mean, okay? A simple average for the time series. So this is basically the R code. You can type it in your console later, or in R script, or sorry, R markdown. And if you run this line of code, this is what you get. So basically, for each combination of region, state, and purpose. If you remember, we have a time series, and then here, if I run this, it will automatically create a name, and here it puts the average of that time series that correspond to this combination. And now, well, this name is not really nice, so what we recommend is, if you do something like this, try to provide a name for it. So how we do it? Well, it is exactly as my line of code is similar to the previous one, but here I use a list function, and then inside this list function, I say, well, instead of just putting a random name, I'll put the name equal to mean. And this is more readable, and then you can work with this later. Okay, so, and as you can see, I don't know, I think my mouse is doing some stuff here. Sorry. Yeah. So if you see here, you have a table, right? There's a table, and then you can work with this table in a way you want. We can also extract some statistical summary. You might be familiar with this 5 summary statistic: minimum, maximum, median, 25 percentiles, and 75 percentiles. So if you want to extract this statistics, so again, you use the same function, and then here, so the main function is features, and then here is the measurement, and then the function you have to provide here is called quantile. And then here I provide what are the different quantiles I want. So I want something between 0 and 1. Again, this is a sequence function that generates the numbers between 0 and 1 and by increment of 25, 0.25. So I have 0, 20, 0.25, 0.50, 0.75, and 1. And then 0 here is actually the minimum. Well, we can't see here, but there is a column there for 100, and 100 is maximum. So if you are interested in extracting this simple statistics, this is the function you have to use, and this is the way you have to do it. So these are like some simple statistics, but now we can also go and look at some features related to autocorrelation. Well, you might be familiar with autocorrelation because we discussed them in time series graphics. So in autocorrelation, what we are interested in is to look at the linear relationship between different periods of the same variable, right? So that's one thing we can extract, and we can have it for different legs, leg 1, leg 2, any leg. We can also have something that is the sum of the first 10 squared autocorrelations. So we first get the autocorrelation for first 10 legs, and then following that we can calculate the squared of each leg and then calculate the summation of this. And this is something that is a useful indication of whether the autocorrelation is significant regardless of the legs. We can also calculate the autocorrelation of transformation of a time series. And then we will discuss about this later when we talk about ARIMA in that chapter corresponding to ARIMA. This is more about having a stationary or non-stationary time series. So if you want, you can transform your time series and then calculate the autocorrelation of the time series as well. We can do it using a function, we call it differencing, but again, this is the name of the function we need to use as well. And if you use just one difference, so the differencing the data, by differencing data, we create a new time series, and this time series consists of the difference between consecutive observations. And then following this, we can calculate the autocorrelation of this. Somehow, this is the way to make a non-stationary time series stationary. Again, without going into detail, because we cover them in ARIMA, when you have a stationary time series, it means mean variance and autocovariance doesn't change over time. It doesn't depend on a time. It doesn't matter where you look at this over time, is more or less the same. So you can, an extreme case of this, you can think about a stationary time series as a like horizontal line with some small random variations. So we can also calculate this and then extract the features. We can calculate two differences. Okay, we calculate this difference once, and then we take that new time series, and again we calculate the difference twice. Then we can also look at the autocorrelation of that as well. The same way, we can also look at the differencing between different seasons. Because if you look at what we do here, this is the adjacent observations. If we do one differencing, so we look at the the change of the time series. But here, if you do the seasonal differencing, we look at the changes actually over year. So if I have like a monthly time series and I do a seasonal differencing, so I have to calculate the difference between January and previous January, February and previous February, March, previous March, and so on and so forth. So this is, again, something we can calculate, and we can calculate its autocorrelation as well. So the function to calculate the autocorrelation features is called fit_ACF, right? So this function will return the following features: the first autocorrelation coefficient for the time series, the sum of square of the first autocorrelation coefficient, the first autocorrelation coefficient from the difference data, and the sum of square of this difference time series, the first autocorrelation of the twice difference data, and then sum square of that time series, which is a difference twice. And then for the seasonal data, the autocorrelation coefficient at the first seasonal leg. So if you put it in the R code, this is how it looks like. So you have the tourism data, then we want to extract features, the features related to this measurement, and then here this is the function. And this is the output of this. So if you run this code, this is what you get here. So in each column, you see that we have all the features we have discussed here. Now, another features of the time series that we can extract is related to decomposition. And probably this is, I mean, autocorrelations are very interesting as well, because they can tell us a lot about the characteristic of time series. But STL features are important because, as we can see it will give us information about the strength of trend and seasonality in the data. This title must be different, so I have to change the title. I forgot to change it. So here, of course, we have a decomposition because the extract of these features are based on the STL decomposition. So, and we have discussed this in chapter 3, but just to make it simple, we can decompose the time series into a trend, a seasonality, and to a reminder. And following this, we can measure the strength of trend and measure the strength of seasonality using this equation, right? So here, the strength of trend is the maximum of the range between 0 and 1 minus the variance of the reminder divided by variance of deseasonalized data. So I have here the trend under reminder. There is no seasonality here. So what happens is if you have a time series with a strong trend on it, so you will get actually a measure that is very close to 1. Because this part for that time series with a strong trend would be very small, and that would be big. So that would be very small, and then 1 minus very small becomes something close to 1. And then the maximum of 0 and something close to 1, again, is something close to 1, right? So that tells us, that measure that tells us how strong is trend in the time series. So in the same way, we can also measure how strong is the seasonality based on STL decomposition. So again, if this measure is very close to 1, it means that time series has a strong seasonality, and if it's close to 0, it means that the seasonality is not very strong. We can extract many other features, including peak and throw. So if you look at the seasonal peak, it measures the timing of peaks. So which season, depending again on the granularity of your data, you may have monthly, quarterly, daily time series, but it tells you which season contains the largest seasonal component. And seasonal trough measures the timing of troughs, so it tells you which season contains the smallest seasonal component. You can have another measure called the spikeness that measures the prevalence of spikes in only the reminder component. So I'm not sure how this could be useful, but you can maybe refer to the book and see whether this is something you might use in your data set or not. So another measure is about the linearity. So the linearity measures the linearity of the trend component of the STL decomposition. Again, this is only about the linearity. If you have like a non-linear trend or a piecewise trend, this is probably not a good measure. So we have curvature as well. That measures the curvature of the trend component, similar to the previous one, but instead of linearity, we look at the curvature. And then we have also the first autocorrelation coefficient of the reminder series. So in ACF, we had the ACF of the time series, the original time series, but here we can also have the ACF of just the reminder part. And then we can have also the sum of square of the first autocorrelation coefficient of the reminder series. How we extract them using R, again, we take the data set, in this case is tourism, and then this is what we had previously. And what we need here is just to provide the function that is corresponding to the features we have discussed in STL. And in this case, it's called feed_STL. And here, for each time series, we can have the strength of the trend, strength of seasonality, and all the variables, all the features we have discussed in previous slide. If you look at for example, the example of Australian tourism data, but you can actually take this and do it with any data. For example, in the past, I have done it with M4 competition data. Unfortunately, I didn't have time to show you an example of that. But For example, in M4, because we have many time series, 48 in total, we have around 100,000 time series, then it is very interesting to go and extract the feature of those time series and then explore them. Here we just look at the tourism data. It has, I think, 300 and something. I'm not very sure, but I can check it here if you like. Let me see. Yeah, tourism. So here we have 304 different time series. Okay. So and what we do is, well, again, we take we extract the features based on STL, and then what we do here, we use ggplot. I think one important thing we have to emphasize here is, because the output of this function is a tibble, it's very easy to work with tidyverse functions, ggplot, dplyr, any other package in tidyverse. So here we want to to plot the trend against seasonality for all the time series we have in our data set in tourist. So we put the strength of trend in x-axis, the strength of seasonality in y-axis, and then we give different color to different purposes, because we have different purpose of the tourism. It could be holiday, it could be business, and the others. And then here we create a geom plot, and then by using the facet wrap, we create different plot for different states in the data set. So if you run this, this is what you get. I mean, what is important to highlight here, again, it is x-axis is strength of trend and y-axis is strength of seasonality. Well, it is crystal clear that the green color, which is corresponding to holiday, it's always higher, because this is changing from 0 to 1. So in almost all of the states was, here it's not actually, we have only 4 time series, so it's not, we can't see it. But for the rest, you see that it is crystal clear that we have a holiday that is, the seasonality is high for holiday purpose comparing to the rest. And it makes sense, because if you look at the time series of this, you'll see that is affected by seasonality. And we know the reason is not surprising at all. So this is, so each point here is corresponding to one time series. Okay, so this is something you need to remember. And then for that particular time series, so we have its trend and its seasonality. Again, if you look at the trend side, so most of them, they don't, the strength of trend is not very high, but here in Western Australia, the trend is pretty high comparing to the rest of the regions. So you can extract this information, like the features, and you can create any sort of plot that you're interested in, but probably this is a plot that makes more sense if you're interested in trend and seasonality in your data. You can do any sort of manipulation you want. For example, in this example, you want to identify the most seasonal series with the data set of Australian tourism data. So here what we do is we take the same function as previous one, and then here we filter the seasonal strengths to be equal to the maximum of the seasonal strengths. And then following that, we have to join it to the original time series, and then we can create a ggplot. And if you run this, again, we can extract the most seasonal series with this data set. Well, in the same way, you can extract any sort of time series you are interested in from the features. Well, there are many other features that you can use. So the features we have covered so far, they're very helpful, especially, I mean, we know trend seasonality and autocorrelation. They're very helpful because they can highlight some key features of the time series. And those features can be used later for forecasting, of course. But there are many other features we can extract. I think in total we have 48 different features we can extract from time series using FIS package. So some of them are highlighted here. Well, I don't really know some of these features. I have never used them, but some of them could be interesting as well. For example, this one is interesting because it can highlight the forecastability in a time series. So by forecastability, I mean how easy or how difficult it is to forecast a time series. Okay, so if it is easy, I think it is close to 1, and if it's difficult, it is close to 0. But you can check it in. Let me check it in FIST in the book, because maybe I'm not 100% sure. Or if you can help, you can just please let me know. I think if I go to other features, yeah, I don't know what I said, but forget about what I said. So what it says here is this, this feature tells us if it's close to 0, so it means this is easy to forecast. Well, it makes sense. 0 is easy to forecast. And if it's difficult to forecast, then it is close to 1, okay? So this is also interesting because you might be, you have many different time series. An analysis like this can tell you what percentage of your time series is difficult to forecast, and maybe you may need to spend more time on those time series. So close to 0 is easy, close to 1 is difficult. We can also extract the coefficient of Hurst, and this will calculate the Hurst coefficient of the time series. And this is something related to autocorrelation as well. So because this is the measure of a long memory, and a series with long memory will have a very high positive autocorrelation for many legs. We can also extract different statistics, including Box-Pierre and Young-Box here. So these two different statistics, again, we use them when we talk about RIMA models. These two statistics will help us to determine whether the time series is stationary or is not stationary. We had FIST ACF, we can have also FIST PACF. So, all the measures we extracted for the ACF, we can have the corresponding measures for partial autocorrelation function. So if you are interested in that, this is what this function helps you to extract that. We can also have, again, a unit root test. And this unit root test will also help you to determine whether the time series are stationary or not. And there are, I think, other things corresponding to this. So here we have unit root number of differencing, and then unit root NS differencing. This is something, again, related to these two statistics. And then here it will tell us about how many differencing you need to make your non-stationary time series stationary. This will tell us about the seasonal differencing, and this is just what we call as a differencing, order 1 or many orders. So this will give us a single number, and so how many differencing you need. So this function, var underscore tilde mean, this gives the variance of the tilde means. So what does that mean is it's a kind of, we create a consecutive non-overlapping block of observations, and we calculate the mean of each block. So you can think of as a block or as a window. So we calculate the mean of each window, and we see whether the mean is changing from one window to another one. We can have something similar to this, but this time for the variance. So this will also be helpful to see whether the variance is changing or not. We can have something again corresponding to what we discuss here, but this time our focus is on the shifts. So we can look at this shift underscore level max to find the largest mean shift between two consecutive window of a time series, and then this shift level index will tell us the index of that largest mean shift. We can also look at the shift underscore var underscore max. This is similar to this one, but instead of looking at the level, we look at the variance, and then we see what is the largest variance shift between two consecutive periods. These are helpful, this sort of measures, if you're interested, in see how volatility changes over the time series, how variation changes in the time series. We can also have shift underscore KL underscore max, and this finds the largest distributional shift. Again, this is based on a metric or a test. I don't know. I'm not familiar with this. So if you're familiar with this, let me know. As I said, unfortunately, I didn't have time, to investigate more about, different aspects of this. But I think this is something I need to know what is this about. So this will, again, it will provide the index of this previous measure we discussed here. We have another feature called n crossing points that compute the number of times the time series crossed the median. We can have also the longest underscore flat underscore spot feature that computes the number of sections of the data where the time series is relatively unchanging. Again, this is something that corresponds to stability of the time series. So if it's low, it means it doesn't change a lot, the time series. We can also have stat underscore arch LM. Again, this is a feature that returns the statistics based on this statistical test, or this is a paper. I'm not familiar with this as well. I have never used arch models before. So again, this is something you might investigate. And then finally, there is, I think, again, there's a typo here. I need to correct it. This is also a measure that computes the optimal parameter for the Box-Cox transformation. So again, this is something we discussed in the composition. This will also give you the optimal value for that transformation. Okay, so there are many features. Again, what you need really to do is to see which of these measures make sense to you, which are these measures are helpful to explore your data set. So again, I think autocorrelation, partial autocorrelation, trend, seasonality, they are very helpful. Entropy could be very helpful as well. Because it tells you things about how easy or how difficult it is to forecast the time series. This sort of thing, we will come back to them later. So again, as I mentioned, these are about being stationary or non-stationary. Well, these two things can also tells us about the white noise. Again, in chapter 2, we discuss about the white noise process, which is a process with no autocorrelation. But we will discuss, a couple of these features in the other chapters as well. So we refer to these features as well. But I think it's important to reflect on these features and see which one makes sense to you to help you to explore the data and their characteristics. So, well, finally, in the last section of the book, we can explore a little bit further the Australian tourism data using these features. So what happens here is, instead of providing a function that tells you which of these features you want to extract, is it related to ACF or STL or PACF, here if you provide this, basically, this will extract all the features of the time series. Okay, so if you want to extract everything, then, and as I mentioned, I think these are 48 different measures. So you can extract everything, and then what you need to do later, because this is a table, right? So you can use all the skills you have in tidyverse to explore different aspects of the time series. For example, while you can create any sort of visualization, really, it is not very clear here. But if you go to the book, you see, extracting these features, they give us some good understanding of the data. Here, we plotted the data for a purpose and giving different colors to different purposes. For example, here is the strengths of seasonality. If you look at the box plot here, it clearly says that for the holiday, holiday is different from the other type of purposes, business or others. It is not, again, very clear here, but if you go to the book, you will see that one of these bar charts, it's about pick, and another one is about throws. And then again, you see that, for example, the pick for the business purpose is occurring in Q4, while this is different for holiday. It's happening in Q2, right? So you can, I mean, the idea here is not go through everything here, but the idea is just to tell you that you can extract all the features, and you can look at every any aspect of that data set that you're interested in to provide important insights. So I think this is, if you want to extract this like 48 features, it's difficult to look at many of them at the same time, right? Just a handful of them probably is possible, but you can't look at every single thing and visualize them at the same plot. So that's why if you have many time series and many features, one way to do it is to use dimension reduction techniques. Again, this is something I haven't used it in the past, so I'm not very familiar with this. But there is a paper, there is a reference in the chapter. If you want to know more about this, you can, I think, go and read this. I was planning, to be honest, I think for at least a couple of months now, to go, because there is a workshop in this. Let me see if I can find it. It's I need maybe to. I think it's here, yeah. So this is about dimension reduction with R. I didn't actually have time to go and do it, but I will share it with you here if you want. Maybe this is an additional information, so you can. Let me see where I can. I'll share it later. I can just find the chat room now. Okay, so let me go back to my slide. So with this dimensional reduction technique, you can somehow reduce the dimension of the time series in terms of all the features, because we have 48 features. And if you want to look at the characteristic of many time series with all the features, this is one way to go for it. And then one way to do it is using principal component analysis. And then with principal component analysis, you can somehow divide the characteristic into two different categories. And then this gives the linear combination of variables that explain the most variation in the original data in one category. And then we can compute the principal component of the analysis for your data set. So we create two different principal component categories, one with the variables that explain the most variation in the data, and another one with the features that has less variations. And then these two categories are not correlated as well. So to extract the principal compute analysis, this is the function we are using here. For example, for the tourism data, here we extracted all the features, 48, and then we created this two principal compute analysis 1 and principal compute analysis 2. So what is highlighting here is, so here, I mean, to summarize this, basically we have, for this one, it uses some of the features that are explaining the most of the variations in the data, and then this one is the rest of the features. So what is highlighting here is, first of all, it tells us for this particular figure that holidays are quite different from the rest of the time series. So each point here is a time series. So holidays are very different. That's one thing we can say from this data set. Another thing is, we have some unusual observations as well. So this dimension reduction, and in this case, PCA, it tells us about, okay, there are some points that are unusual. So if they are unusual, and then, you see, for example, PC1 here is more than 10 for these 4 different points. So maybe you can also go and explore those unusual observations. And they say, well, I want actually if the PC1, fitted PC1 is greater than 10.5. And then select all the variables that you have in the data set. So this is the outcome of, if you run this is the production of this code. And if you want to plot it, you can also plot those time series that are a bit unusual. So you can observe them and then see why they're not actually like others and quite different from the others, as we can see them. Yeah, I think that was what I wanted to share. It was, as I said, I had to prepare them this morning in Rush, so I didn't really have time to reflect on many things, but I hope that was helpful. If there is any question, please let me know.
So Professor, one question is, we have a lot of features with shift, right? Shift level max,
yeah.
Variance, etc. So when we say shift, does it mean the difference?
Yeah, exactly. So it's like, it's like, so let's imagine you have 24 observations, and let's imagine you have a block of 12. So basically you split your 24 observation to first 12, first block, and second block of 12, right? And then if you look at the mean, so you look at the mean of first block and mean of the second block, and see then how means changes from one block to another.
Okay, makes sense. And number 2 is, there were some features which are related to the autocorrelation function of remainder component.
Yeah. So I say how ICFF reminder component could help. Yeah, so, because if you remember, what is in the reminder? Well, in the reminder, it's not about random variations only, okay? It is, because if it's completely random, then the ACF will tell you, okay, there is no significant autocorrelation there. But if you remember when we discuss about this, I said in reminder, we have everything that is not trend and that is not seasonality, right?
Correct.
So we may have some important information that is not trend and seasonality related to, I don't know, some sort of events that are in the reminder, and that those things could be helpful in using in the forecasting model. And then, well, I haven't used this ACF for the reminder, but my understanding is if you have an ACF that tells you, well, there is some significant information in the data, right? It is not completely random, then you have to think about what are those information and how you can account for them in your forecasting model.
Okay, thank you, understood.
Is there any other question?
Nothing else from my side.
Okay.
No, thank you.
Okay, I'll stop sharing. Let me send you that. Let me send you the link to this workshop. This is not what I wanted, this one. But there are a couple of, I think, again, I will see if this is what I wanted to, I just Google it, but I have it somewhere. I just need to find it. So maybe this is something you can go and have a look. This dimensional reduction things. I think these are interesting if you work with many time series. These are the sort of thing probably you have to look at.